Good morning students. Today we are going to discuss few important topics from the chapter 3, that is current electricity. Now the first topic which we are going to discuss is your electric current. I think most of you know the definition of electric current. It is nothing but the rate of flow of charge. So here little bit elaborately we will discuss this topic. Let me read out. Electric current is defined as the amount of electric charges flowing through any cross section of a conductor per unit time. So if we consider this diagram, you see this is a conductor and a source is connected across the conductor with a key. Now when you switch on the key, what will happen? The electrons will experience a force, and this force led the electron to move through the conductor. So if we count the number of charges or the amount of charges that passes through any cross section of the conductor, we have drawn a cross section by giving the shaded region. So if we count the amount of charge that passes through this cross section in unit time, then that is nothing but is your current. So definitely it is the source which gives the force or pull the electrons to pass through this cross section. So let q charges process through cross section of a conductor in time t. So if it happens, then current will be your total charge by total time, that is your I equal to q by t. Now SI unit of electric current is your ampere, and it is denoted by capital A, and 1 ampere can be defined from the expression I equal to q by t. 1 ampere equal to 1 coulomb by 1 second. So if we consider 1 coulomb of charges passes through any cross section of a conductor in 1 second, then that is nothing but is your current 1 ampere. So what we have written, if 1 coulomb of charges flows through any cross section of a conductor in 1 second, then it constitutes 1 ampere current. So this definition as well as the topic, I think most of you have got in lower class. So here definitely we are using the term electric current to define some other topic apart from the definition and the expression. So this is the next topic which you are going to define, electric current in conductors. So two figure we have drawn, figure 1 and figure 2. So in figure 1, what we have trying to show, there are n electrons and all electrons are moving randomly in all direction. One is moving with the velocity u1 vector in up, another one is moving with u2 vector in down, and another one is moving in some other direction that we define by u suffix n vector. So there are n electrons. Here for simplicity of the diagram we have given 3 electrons starting with u1 u2, and the end one is your un. So you see all electrons are moving randomly in all direction, and the energy acquired by the electron is nothing but the surrounding temperature. So the movement is due to the thermal energy. Now you see if we consider a conductor, so what happens inside the conductor, the electrons move randomly in all possible directions. So if charge particle moves, then definitely you must have to experience current, no? But in practical we are not going to experience any kind of current if we touch a conductor. Definitely I think most of you have tried. Suppose if you keep a iron rod and if you touch the iron rod, do you experience any kind of current? I think no. Now what's the reason? Suppose if we consider n electrons, and number 1 electron is moving in a particular direction, in upward direction, which we have shown in the diagram. So there may be the probability that another electron which is moving with the same magnitude as that of u1 vector but in opposite direction. So if it happens, then u1 vector and that opposite directed electron, definitely the velocity cancel out and ultimately the velocity is 0. Similarly, it happens for u2 vector. u2 vector is the velocity for the electron. Now there may be the possibility that another electron moving with the same magnitude as that of u2 vector but in opposite direction. So it happens, if it happens, then definitely the resultant velocity is 0. So in this way, for every particular electron moving in a particular direction, definitely there corresponds another electron which is moving in opposite direction with the same magnitude. That's why the resultant velocity goes to 0, and finally you can consider for n electrons which are moving randomly in all possible direction, the ultimate resultant velocity is 0. So if ultimate resultant velocity is 0, then definitely you can consider that there is no current. But you will experience current in the conductor if you connect a source across the conductor, so which we are trying to show in the figure 2. So when you connect a source with the key, so if we close the key, what will happen? All the electrons move in a particular direction. Yeah, with different velocity. Definitely we are trying to show, one is your v1 vector, another one is your v2 vector, and the final one is your vn vector. So all electrons are moving in a particular direction. So definitely when all the electrons are moving in a particular direction, definitely it will experience some kind of resistive force, and that resistive force we are going to discuss later on. Now all the electrons moving in a direction which is opposite to the direction of the electric field. Electric field is from left to right, but the electrons are moving from right to left depending on the terminal of the source. Now what we have written, please read out. In a conductor, free electrons move randomly with a thermal speed at room temperature, so which is happened in figure 1. On applying electric field, the electrons move in a particular direction opposite to the direction of electric field. So definitely the electrons are moving in opposite direction that of the electric field. So when the electrons move in a opposite direction and when the electrons move in a particular direction, so what other things may happen? There may be the collision, and definitely if an electron collides with another electron, then definitely the electron which collides with the electron which is in front of it, definitely it moves fast, but the later one recoil. Return one means the later one moves back. That is your recoil velocity. So there may be the possibility that there is a very small time interval during which there is no collision, and that time interval will define as a relaxation time. I think most of you understood what is relaxation time. So you can assume that electrons are moving in a particular line. There may be the possibility of collision. So let me consider a particular electron collides with an electron which is in front of it. So when it collides with the electron which is in front of it, then definitely after the collision that electron will move back. Now when the electron will move back, there may be the possibility that another electron will come and strike on the electron which is recoiling back. But there may be the small time interval during which there is no collision, and that time interval is nothing but the relaxation time. So this part will come across afterwards during the definition of the drift velocity. So next topic, drift velocity. It comes from the figure 2. What we have written, drift velocity is defined as the average velocity with which free electrons in a conductor get drifted in a direction opposite to the direction of electric field. So in figure 2 we have specified with v1, v2 and vn vector. So the average velocity is nothing but is here, we have denoted v suffix d. Small d is nothing but the drift velocity. So this is nothing but the average velocity of the electron, v1 vector plus v2 vector plus dot dot vn vector by n. This is the average velocity due to the application of the electric field, which we define as your drift velocity. So our job is to define the expression for the drift velocity. So in absence of electric field, as seen in the figure 1, u vector equal to u1 vector plus u2 vector plus dot dot un vector by n equal to 0. And in presence of electric field, all electrons moving in a particular direction is specified by v1 vector. So we are going to use the expression for the equation of motion, that is v equal to u plus at. So v1 vector equal to u1 vector plus a vector tau 1, v2 vector equal to u2 vector plus a vector tau 2, like that, dot dot, finally vn vector equal to un vector plus a vector tau n. So where tau 1, tau 2, dot dot tau n are the relaxation time for n electrons. Okay, relaxation time which we have defined just now. So definitely as the electrons are moving opposite to the direction of the electric field, definitely the electrons will experience a force, because due to the presence of the electric field, and that force comes from the Newton's second law of motion, that is your F vector equal to m a vector. So F vector you can write minus e vector. It comes from the definition of the field intensity. So a vector equal to minus e vector by m. So drift velocity, we are going to use this expression vd vector equal to, but we are going to substitute v1 v2 plus dot dot vn. So if we substitute from equation 3 this term, u1 vector plus a vector tau 1, and finally un vector plus a vector tau n, we are simplifying the expression by writing only the extreme n term. So in simple mathematics, you take out the u1 vector plus dot dot un vector by n, plus a vector tau 1 plus dot dot tau n by n. So first term goes to 0 due to the equation, due to this in absence of electric field, equation 2. So ultimately you are getting a vector tau. So you are supposed to substitute a vector from equation 4. So if you substitute, then it comes out minus e vector tau by m. Tau is nothing but the average relaxation time for an electrons. So this expression is very important. Please go through this topic, and before winding up this class, please try to download the videos at the very starting of the class or at the very day of the class, but don't keep the work pending, because there may be the possibility that due to technical reason the videos may be deleted. So it's your prime duty to download the materials at the very day of your class. So this is all about. Please go through this topic and find out your doubts. Thank you.